So we're going to go ahead and get started for the second JQI seminar. I'm going to introduce our speaker, Kevin Cox. He did his undergrad at William & Mary and then went to University of Colorado at Boulder and worked with James Thomson on atoms and cavities and spin squeezing experiments. Some really awesome physics there. Then he moved to the Army Research Lab in Adelphi, just up the road, for a postdoc, and is now a permanent physicist there. And he'll tell us a bit about what's going on at ARL. Great.
Thank you. It's a real pleasure to be here, and I hope that this talk can be a lot of fun. It's informal, and I hope feel free to ask questions. I hope to talk a little bit about the Army Research Laboratory. I really like working there. I like doing science there, and a little bit about at least one of the projects we do. I won't talk about everything we do. And I guess I need to stand kind of here-ish. No, this is fine. And then to go forward, I do this. Actually, I didn't ask that. Here we go. Okay. So here's a picture of our group. Some of the guys are in the back there. David, you want to raise your hand? That's my colleague, David, also a staff scientist in our group. You can see the picture. We're kind of a bunch of misfits up here. We're only a few miles down the road. We have existing collaborations with the University of Maryland through the Quantum Technology Center. And, the Army Research Laboratory is really the Army's only lab for fundamental science. We have a lot of engineering development centers, but ARL is the place where really the basic science happens. And that's the reason why I like working there. I want to actually, before I go on, I want to just say a little bit more about the Army Research Lab. I think before I started, I didn't know a lot about it. I think a lot of people have questions about what it's like to work for the military. One of the things is there's one thing that I'm thankful for, which is that overall, optical and atomic physics, quantum physics, does not have a lot of lethal applications. So, most of the time, spectroscopy grade lasers are not extremely dangerous, except for probably your eyes, which we try to mitigate those dangers actually. And actually a lot of the real technology that has come from quantum science and atomic physics is for timekeeping and positioning and navigation and information science. And so, that's something we don't have to worry about too much on a day-to-day basis at ARL. There's not a secret door. If you come over to our lab, I encourage you to visit. If you're a US citizen, it's very easy to come visit. You can come tomorrow if you like. But there's no secret doors. You go behind the secret door and all the bad stuff's back there. There isn't that door at ARL. It's a lot like many of you have experience working at NIST, at the National Institute of Standards and Technology, and ARL is very similar from my experience in flavor to working at NIST. Has a lot of the same advantages and annoyances as working at NIST. And then I think there's another aspect, which is the United States defense sector has really been quite faithful to fundamental science over the years. We really would not have chip scale atomic clocks if it wasn't for the Army's commitment to atomic physics. We publish everything we do at ARL. We publish papers a lot. I can't say they're good papers, but we at least get them out there. And that's a lot because, ARL really is committed to just science. And we do science to promote our national security, but we also care about the science. And then the last piece, I'm almost done. The last piece is that we can't be too naive to think that really we would be here without the United States defense system. Now, we all know that the United States is not perfect. We never will be. I think that's just glaringly obvious to all of us at this point. And but at the same time, there's been a lot of good that's come out of the defense research. And a lot of that good is now just in the public sector for the public good. So all that being said, I think to some degree, when a lot of us, and this is me included, question working for a military lab, I think some of that's a little bit overblown. Okay, So, of course, I'm going to get to the hiring pitch in the end. So, this is just all a setup. Okay, the quantum legacy continues. I want to talk a little bit about, before I get started, about why the Army is so invested in quantum science. And by the way, we are. One of the Office of the Undersecretary of Defense Research and Engineering, one of their top 9 research priorities is in quantum science. And so that's sort of at the Pentagon level. That's a public document you can look up. And one of the top priorities is in quantum, and I think for good reason, because we wouldn't have a lot of the technology we have today if it weren't for quantum mechanics. The sort of first quantum revolution from the earlier part of the 1900s, led to like the first transistor. That's one of my favorite things. The first transistor and band theory and our phones and all of our information equipment is really born out of the first quantum revolution. And a lot of really wonderful technologies, things that the Army cares a lot about, like radars, came through really our understanding of light, our understanding of coherent light in the form of masers and lasers. And then, the fact is that the quantum revolution hasn't really ended. It's continued. And I would say in the past decades, that quantum revolution has really been in understanding how to control quantum matter at an exquisite level through atom cooling and trapping, and through being able to probe in many body entanglement systems that are entangled in ways that have no classical analog. Of course, many of you here know about all of this work. This is where we live. And this is, there's steeped tradition here at JQI and the University of Maryland. And many of us are lucky enough to have worked with the folks that have really started this. So this is a very unscientific slide, but it can be useful because you can really describe quantum technology. You can sort of roughly quantify it and say, well, we have all these technologies that I would call quantum technologies, like your iPhone and laser pointers. I don't actually know what this thing I'm holding is here now. I have no clue. I don't think it's a laser. It may be though. Does it have like a quantum IMU? I don't know. Anyway, you can think of those as things that are described by quantum mechanics. That actually could be the whole world. If you wanted, you could call anything a quantum technology, but you wouldn't have to, because a lot of those things you could describe as harmonic oscillators, or capacitors and inductors and things like that. Then there are things that you might call quantum 1.0, which are my favorite aspect. And we can all kind of argue about what quantum 1.0 is, but to me, quantum 1.0 is things where you're using the fundamental nature of quantum particles. Atomic clocks, if all atoms weren't identical, quantum atomic clocks just wouldn't even make sense. And so these are really powerful technologies, but nonetheless, they don't use the thing that's in quantum 2.0, which is quantum entanglement or quantum correlation that is inherently non-local. For instance, as shown by a Bell test or something like that. And these are the technologies, I would argue, that really haven't shown anything so far, but we hope they do. We're here because we hope that entanglement becomes useful one day. And we believe, most of us believe, that entanglement is an untapped resource for long distance, technologies that rely on long distance correlation, but also technologies that rely on many body quantum information. Because again, most physicists believe that when you have many particles entangled with one another, there is an informational component that has no classical analog. Okay, so that's really our job, is to drive this forward even more. What are the capabilities that the first and second and third quantum revolution will bring? And I at least take it very seriously. I think that real technology will come out of this, and so we're interested in understanding the basic foundations of the world better, and we're interested in making new technologies based on it. And so we're not here to play around. We're not here just to do science experiments. We're here to understand the world better, and we're here to actually show that it can be useful. So that's our call. So that brings us to my branch. One of the ways to make a theme of the branch I work for, it's the Quantum Science and Technology branch at ARL, is efficient light matter interfaces. I work in the sort of cold atoms and warm atoms physics group. We also have significant groups doing solid state defects. We also have Joe Britton, who many of you know, Dr. Joe Britton, who actually has his lab based here at Maryland and focus on trapped ions. And again, I happy to tell you more about the branch overall if you have questions. Okay, so now moving on to the, how am I doing on time? Doing okay? Any questions before I move on to a specific experiment? That was kind of all overview. Okay. So today I'm going to talk to you about our work building Rydberg atom-based electric field sensors. So how should you think about this? This is work that is a little bit more applied in a way. The goal is to take all the giant Pandora's box of technology that we use using antennas and transmitters and receivers, and to what degree can we replace as much as possible with atoms? And so think of these objects as atomic clocks, but instead of measuring time, they are measuring radio frequency fields. And Rydberg atoms are a really exciting platform to do that. So we're taking some of this simple atomic technology and seeing how it can be used. Okay, so yeah, so maybe let's just quickly talk about what a Rydberg atom is. A Rydberg atom is an atom where one of the valence electrons is excited up to a highly excited state. We usually write down that state as having a high principal quantum number n. You can really think of all of the properties of this atom, and the advantageous properties come from the large dipole moment that you see when you do that. You can go to the Bohr model of the atom. It tells you that the dipole moment of the atom scales like the charge of the electron times the Bohr radius times n squared. That's kind of the average separation of the electron from the nucleus times its charge, of course. And if you apply a DC field or some field that's really not near an atomic resonance, then the amount of induced dipole you get is given by the polarizability. That actually goes like into the 7th in a Rydberg atom. And so we use both of these properties to build systems, atomic sensors that are sensitive to electric fields, both at DC all the way up to, in our case, we're really interested in DC up to hundreds of gigahertz. And of course, this is what the shiny eye candy looks like, with really no scientific, very little scientific, thought. So we're not the only people who do this, and we're not the first people who do this. And so I want to give credit to some of the other groups that have thought about this problem over the past decades. People recognize the large and strong interactions you can get with electromagnetic fields from Rydberg atoms for a long time. I would say in the past 5 years, this field has really, the applied area of this field, saying, can we actually, not just our Rydberg atoms, do they have a large dipole moment, but can we actually build devices based off of them? That field has really exploded in the last 5 years. And there are multiple companies now that are trying to actually build deployable systems based on Rydberg atoms. So it's an exciting field to be in right now. Here's what a basic experiment. So before I'm going to get into some of the details about sort of the physics of how these sensors work. But before I do that, I just want to just show it to you. But just have a little bit of show and tell. So here's the basic experimental diagram, also in a little bit too fancy of a graphic, but more fancy than's needed here. But I think it works. So this is the basic diagram. You have these are vapor cell containing rubidium atoms. In this case, you could really probably use any atom that has one valence electron. Even atoms that have two valence electrons would probably work. But here we use rubidium, which is many of our favorite one valence electron atom. And you just shine however many lasers you want to excite it up to a Rydberg state. In this case, we use two. We use a laser at 780 nanometers and a blue laser at 480 nanometers. They counterpropagate, and I may explain why, but it's not that important. And then we also shine a radio frequency field in green. That's the thing we want to measure. And the information from that radio frequency field gets encoded, in our case, into the what I'm calling the probe laser, but that's the 780 nanometer laser. And we detect it on a photodetector here. So it's really a microwave to optical conversion experiment. It's using spectroscopy, very basic spectroscopy methods, the same that you would use if you want to build any kind of atomic sensor. And I'll talk about the details a little more in a minute. But I want to show you our lab demo. This is our favorite lab demo we showed to the generals. The generals, you know, the generals really like to see it. The generals don't read papers, and that's fine. They shouldn't. But they really like to see something. And so this is a very simple demo. This demo doesn't show you that these systems are actually better than any other technology, but it just shows you that it's there and it works. So here's what we do. And by the way, this particular one, I use this one because we have a video of it. It's a little bit overcomplicated and meta. So bear with me for just a minute. So we take the system that I just showed you, but what we do is we take our transmitter, this is the microwave transmitter that I showed, and we hook it up to a 17 gigahertz synthesizer. So we have a 17 gigahertz tone that we're sending at Rydberg atoms. And then we take just a video camera, and we take the output with just an analog output, and we take the analog output of that video camera and we plug it into the modulation port of that 17 gigahertz synthesizer, okay? So we're taking the video and we're just modulating a 17 gigahertz carrier really simply by just plugging into the modulation port. We send it at the Rydberg atoms. That gets imposed onto a laser beam, onto a photodetector. The demodulation of the 17 gigahertz is happening sort of in the atoms. That's the way to think about that. And then we send that to you know, an analog screen. And so we're making a video link. This is a video link experiment where we're videoing the video link. So it'll be a little weird, but that was this demo. Okay, here we go. And don't worry about the sound. So there's the camera right here. There's the rubidium cell. There's the screen videoing the video link. Here's the microwave horn right there. So you've got 17 gigahertz coming there. It's blasting towards the rubidium. So it's a very simple experiment. Blue laser is going this way, down. The red laser is going the other way. We're moving the camera around. And now it could be that we've just plugged this camera into the screen, right? I mean, so this is the worst demo ever. You just took that camera and you plugged it into the screen, but we didn't. I promise you there's a 17 gigahertz source up here, and that we've actually plugged the camera into the 17 gigahertz source. The 17 gigahertz is coming here. And the way you know that I'm not lying to you is because then the hand from above comes and grabs the cell. And so when the hand from above grabs the cell, of course, the video goes away. And then the hand from above puts the cell back in and the video comes back in. And that's really nice. And then I think the hand from above blocks a laser beam. There you go. And the video goes away also. And then the hand from above also will block the horn itself. And you know, hands are made of water, so they block microwaves pretty well. Yeah, there you go. So that kind of just shows you what's going on with the demo. And there's a few, the 780 lasers are over here. The 480 nanometer laser, the nice blue laser, is pretty strong. It's probably a 100 milliwatt laser. It's sitting over here. It's a doubled laser, so it's in a pretty big box. But there's really nothing too complicated about this setup, and that's why it's a good candidate for being useful in real technology. Okay, so let's step back now and talk about the mechanics of Rydberg sensor. Any questions? Okay. And
I can't resist.
Yeah.
It really reminds me of the thing that a lot of us did like 50 years ago.
Oh yeah, totally.
We took a thin layer of reflective material and spoke into it, and it modulated a laser that, you know, so that it was a laser transmission microscope. But of course, as you say, you could have just hooked up a wire.
Yeah, exactly right.
And but obviously it demonstrated something important, which was that you could carry an audio signal. And now you've done the same thing with a video signal. So I assume you're going to tell us why you care.
Yeah. Mhm.
Uh,
Sort of. Hopefully, yeah.
Because, of
Yeah.
course, I mean, when we did that kind of thing was before,
Hmm.
almost all audio communication was actually carried by laser beams.
Yeah, that's right. That's right.
Uh, I mean, today, video information is carried by laser,
Mhm.
but this is different because atoms are in there.
Mhm,
And that's
yeah.
the key thing you're gonna,
That's right.
I hope, tell us.
Yeah, I think so. I mean, I hope I have a satisfactory answer for that, and if not, we can talk more. But that's right. I mean, you could do this with an electro-optic modulator. Many of you work in laser labs, and you have these electro-optic modulators made out of lithium niobate crystals. And if you take that crystal and you hold it up and you shine a microwave through it, it will change the electro-optic coefficient. And again, lots of communication is based on that. And it's that's actually been one of one of the big things we've done over the past few years after we kind of did initial data with this is, why do you want to use Rydberg atoms instead of something else? That's a really important and obvious question. And so one of the important comparison points is actually electro-optic radio frequency sensors. People actually use electro-optic radio frequency sensors for calibrations of high power microwaves, because one of the great things about an electro-optic crystal is that they're pretty strong, they're pretty robust. They can actually handle lots of different frequencies and have high bandwidth. So electro-optic crystals, kind of similar to what you were talking about, Bill, is it's actually used technology all over. And then the question is, are there areas where you would want to use Rydberg atoms instead? So hopefully that's a question I can answer at least reasonably well. I mean, I think the part of the answer is we don't know. Yeah. So yeah, sensitivity is definitely one of the most important. Yeah, I'll talk about it. I'm getting to it. Yeah. Okay, so but before I talk about that, I just want to go back and talk about kind of how I think of Rydberg sensors. This may not be the only way to think about Rydberg sensors, but here's the energy level diagram, which I haven't showed yet. It's always important to have. In rubidium, here our ground state is 5s level. That this is the state of the valence electron. And then the 780 nanometer laser takes us up to a 5p state, where you've just changed the angular momentum of the valence electron. And then our blue laser takes us up to a Rydberg state characterized by N. We can usually pretty easily get to N equals 40, N equals 50, N equals 60, N equals 70, maybe N equals 80. In warm atoms, again, the atoms are moving around at 300 meters per second, and you have this big Doppler broadening, right? Because some atoms are coming towards the laser beam, some are going away. And then there's also interactions, because they're Rydberg atoms, they have a large dipole moment. So not only do they interact with the RF fields, they interact with each other. Those are the kind of things that limit how high we can get to an N, but typically 70 or 80 is pretty reasonable. We ultimately, if you're using a quantum system to detect anything, you usually, most often you are doing something like this. You want to make a wave function that is a coherent superposition. Again, ignore normalizations. I mean, you're never getting that from me. Is the superposition of the ground state and the Rydberg state, and then you're always measuring the quantum phase in between. It doesn't have to be the quantum phase in the exponent here. It could actually just be the angle. If I'd written a cosine of theta and a sine theta here, it could actually be the angle, the population angle instead of the phase angle. But no matter what, you're measuring something about the coherence here. And if you're doing that, you really want to think, oh, actually I have a question. Why have I ignored the P state? Anybody? It's like actual question. Why did I just write the ground state in the Rydberg state? What did I ignore the P state? Yeah. It's never populated, and I guess the reason it's not populated is we don't want it to be populated, because it actually has a very short lifetime. If you want to have a coherent superposition, you need states that don't decay too quickly, and this state decays much quicker than the ground state and the Rydberg state. But then the follow-up question is, why does this state decay more quickly than the Rydberg state? That one's at high energy. You would think intuitively that one would decay really fast, but it doesn't. Why is that? Sorry, it's the next question. You didn't know there was going to be quiz. Yeah, right. It's the reason the sky's blue, right? I mean, it's because, and now, by the way, you know, somewhere in Jackson, you learned that the scattering rate of a dipole, or of a, yeah, the scattering rate of a dipole goes like, you know, omega cubed or omega fourth, depending, I think, on exactly what quantity you're looking at. And I can't derive that on the board right now, so don't ask me to. But you know, that's sort of a fundamental property for dipoles and how they scatter. And so actually, the reason why, okay, the reason why the now, so there's like a missing piece here. The reason is that the overlap, so the nearest available transitions for this in d5 half state are n-1 d5 halves. There are other Rydberg states that you want to decay into, and those Rydberg states are separated by microwaves. They're not optical transitions, and because they're microwave transitions, it's just this fundamental electromagnetics property that says that their scattering rate is lower because of, you know, Maxwell's equations. So okay, anyway, that wasn't a very good description, but
why you use D instead of S?
oh, right, no reason. We can use S.
These have, well, you know.
Yeah, you know, so we can use any dipole allowed transition. We can use the S states, we can use the D states. You can do this with 3 lasers. You can go 5S to 5P to 6S and then up to Rydberg, and then you can go to an F state. You can, it's actually great. There's hundreds of Rydberg states, maybe thousands, tons of Rydberg states you can do. And there's really, yeah, most of the time you go into lab, you actually just kind of choose randomly. You want ones that have large electric dipole moments. The transitions have large electric dipole moments, and you know, you can get into really details, and you know, there's weird cancellations and stuff. But overall, you really just kind of choose. There's not a whole lot to it. So okay, so if you want to, but if you, so we have a quantum sensor between the ground and the Rydberg state. We kind of ignore the middle state because it decays away quickly, and the coherence is really between the ground and the Rydberg state. And then if you do that, it's just like any other quantum sensor. And I think this is important to connect. It could be an atomic clock, it could be a magnetometer, it could be anything. And the fundamental signal to noise limit of this sensor comes from the coin flip statistics, from the fact that you have equal superposition, you measure the state. Sometimes the atoms collapse into the ground state, sometimes they collapse into the Rydberg state. And the best you can do for measuring this phase is 1 over square root of n. And we can actually show in sort of theory-ish papers that that Rydberg sensors are at least, you know, if you define the atom number correctly, of course, because we have atoms, some atoms that are just flying too fast for us to probe. But if you define the atom number correctly, that our sensors are, you know, within a few numerical factors of reaching this limit. And that is really neat to say that even these simple sensors are limited by the quantum collapse of the individual atoms. That's just really beautiful. And of course, if we could entangle all the atoms, there's no way for us to do that. But if we could entangle all of the atoms so that they all collapsed together and in concert, we could reach what's called the Heisenberg limit. And the Heisenberg limit is just if all the collapses are now synchronized so that half collapse up and half collapse down, then instead of describing this sphere in increments of 1 over root n, instead of being able to resolve it there, you could do it 1 over n, because you have n atoms. So the best you can do is have n discrete tick marks on your clock. So the Heisenberg limit, in some sense, is very classical. It's just saying how many ticks do you have on your clock? You have n atoms. You can't have more than n. You cannot have any more than n discretizations on your quantized object. Okay, so we use something called electromagnetically induced transparency spectroscopy, or coherent population trapping, or some combination of the two. Those are very similar phenomenon, but you know, this is a spectroscopy technique that's been around for a long time. But the idea is that you have 2 long-lived levels. In this case, they're the Rydberg state and the ground state, and then you have one level in the middle that's lossy. And if you apply lasers that meet the 2 photon resonance condition, so the energy of this photon plus the energy of this photon equals the Rydberg state, then what typically happens is you find a transparency resonance on the 2-photon resonance. So basically this atom scatters and scatters and scatters until you hit the 2-photon resonance, and then all of a sudden the laser gets through. And the simplest explanation for that is that you can go into what's called a dark state, where there is a state which, if everything is symmetrically oriented in some ideal case, it's just the anti-symmetric superposition of the ground state and the Rydberg state. And if it has a minus sign, then the probability amplitude to scatter from the ground state and the probability amplitude to scatter off the Rydberg state cancel. You can kind of see it pretty easily. If you made an expectation value with this and you set it up just right, you could see that minus sign might cause it to go to 0. And that's exactly what happens. And so that is a very useful spectroscopy technique to build. And that's exactly what we use. That's how these sensors work. It's actually a really interesting question of if there is a better one, if there's a better way to do spectroscopy on warm atoms in a nice compact system. That, it's something we think about a lot. Okay, and so when you do that, you can do two things. So then you just measure the light that goes through. We do it in homodynamic detection, where we can measure the phase or the amplitude of the light. Up here, this is maybe what the transmission would look like as you sweep in this case, as you sweep a detuning. You could either sweep the detuning of the blue laser or sweep the detuning of the red laser. And as you sweep it, you'll see a transmission peak on the red laser, or if you're looking at the phase, you'll see a dispersive. Okay. So then the next thing is that now we want to detect radio frequency fields. So we add one more Rydberg transition. We send in microwaves that are resonant. If the microwaves are resonant with the transition, you see an Otler-Town splitting, or what people typically call an Otler-Town splitting. You can think of that as just the same thing that happens when you connect two harmonic oscillators. In this case, one harmonic oscillator is the radio frequency field. The other harmonic oscillator is the atomic transition. And when you connect those two harmonic oscillators, you get a normalized mode, and you actually see it in spectroscopy. The size of that splitting is equal to the atomic dipole moment times the electric field. So that splitting scales as n squared. Or you can apply an electric field that's way off resonance. And if you do that, you will just see the resonance. You will see this resonance, the EIT resonance shift. And that shift will be proportional to the electric field squared. And we talk about that as sort of being proportional to the DC polarizability of the atom. And we can use either of those phenomena, either on resonance Otler-Towns interactions or on resonance interactions, or just the off resonant polarizability. And we can use either of those. In fact, this off resonant polarizability that scales us into the 7th is quite useful. The size of the shift goes as E squared, and that allows you to build a super heterodyne detector. Because you take this electric field sensitivity, the signal goes like E squared, but you put on two electric fields. So the total signal is E1 squared plus 2 E1 E2 plus E2 squared. And then this middle term we call a heterodyne beat. The noise in this process actually doesn't depend on what electric fields you apply. So in this case, you actually boost up your signal to noise by applying this second electric field. So this is called super heterodyne receiving. This is how basically all modern radio receivers work. But here we're doing it with atoms instead, which is nice. And this allows you to increase the signal to noise ratio. And so the very first experiment we did in the lab on this was in 2018. And we just wanted to show if this sensor, using all the principles that I just showed, if it worked. Could you just send data using a typical data stream format? And of course the answer is it does, and it's really not at all surprising. So here is, as we change the red laser detuning, that's probe detuning on the bottom, we look at the transmission through the cell in just normalized units. And if there's no RF field, you see an EIT peak, and if there is an RF field, it splits into this Otler-Towns shape. So the data is pretty clean. And if you sit somewhere on this spectroscopy feature where you're sensitive to fields, you can find a point where you're linearly sensitive, and then you just set up a communication scheme. In this case, we amplitude modulated the field, And then we measured the phase of the amplitude modulation, and we set up a digital data link by looking at the phase of the amplitude modulation. I would say this was a very simple experiment. We really didn't learn anything new about physics by doing this. But what we did is, maybe for the first time, we thought seriously. We talked about sensitivities. We measured sensitivity. We measured the data rate and the maximum bandwidth. And we thought seriously about, can these atoms actually be useful? And I think this was one of the first times when people really started to think about that. And since then, people have thought about it a lot. So now I'll kind of start getting to the question earlier. Why do you want to do this? Why is this better than just using some other technology like a paperclip and an op amp? So I'm going to skip ahead to answer the question first. We've done work on this theoretically. This is not really going to answer the question very well. One of the great things about Rydberg atoms is that they actually have very well defined sensitivities. You can basically use the Bohr model of the atom to get within an order of magnitude of your sensitivity to any RF field, ranging from 0 frequency up to about a terahertz. The physics is very, very simple. And in fact, you can write down your minimum detectable electric field over that entire range, and it's pretty decent. Of course, it depends on how many atoms you have and all the technical details. But one of the first things we did was we tried to do a pretty in-depth study of what was that signal noise ratio, and this is what we came up with. This is way out of date now. It's only a few years old. But we compared to having a small dipole that's read out through a high impedance circuit. We compared to see that EO, that stands for electro-optics. So we stood for electro-optic receiver. And then we have all these, you see this color bar on the right, and then lots of colorful lines. That was what we thought you could do at any frequency with Rydberg atoms. So up here, you see that it goes everywhere. That's basically the forest of Rydberg transitions. Down is good on this plot, I should say that. Most plots really probably should have made this where up is good, but on this plot, down is good. And so, your best Rydberg sensitivity is this rainbow colored line down here. This is where you can hit dipole allowed transitions. And you can see electric fields in this plot that are, 10 to the minus 7 volts per meter in 1 second. There's a limit down here of thermal noise, which is to say, what would happen if, and this is sort of centimeter. We're kind of comparing everything at a centimeter scale. So thermal noise is kind of what would happen if you read in the field into a centimeter aperture and it was limited by just room temperature blackbody radiation. That's kind of the line you get here. The line that gets down here is just the limit from the shot noise on the photons. The radio frequency shot noise. Actually, these lines cross somewhere in the ballpark of hundreds of gigahertz, terahertz. Yeah.
So it's all about this kind of microwave coverage range, and then you're detecting electric.
Yeah, so we're using transitions that have a large electric dipole moment. So we're looking at electric fields. You could actually imagine going to states that have a large magnetic dipole moment and detect the magnetic field component. But yeah, here we're detecting the electric field component. Yep.
So my question is, have a sensor on that kind of spectrum, sensing the magnetic field. That's what usually radio does.
It can do either one. It really depends. I mean, if you build a half-wave dipole, then you're detecting electric fields. If you build a loop, then you're detecting magnetic fields. So antennas can do either one. Yeah.
If you compare this one with electric field detector,
Yeah.
with the magnetic field.
Yes.
For example, just
Yes.
radio.
Yes.
That is equivalent to the same.
Yes. Yes. Yes.
Of this.
Yeah. You want to know the answer. What's better? So the answer is that if you want to detect a single frequency, so you want to build a resonant antenna-based design, you can, at the moment, even with state-of-the-art Rydberg sensors, you can typically outperform a Rydberg sensor in sensitivity by at least more than 10 dB, 10 to 20 dB. So one way to think about that, here's maybe a more fundamental way to think about that. Here's another quiz question. If you actually take a 50 ohm resistor This is like something you should all memorize. 50 ohm resistor at room temperature, and you plug it up to a voltage meter, and you want to say, what's the voltage noise integrated into a 1 second bandwidth? How much is that in volts? Anybody know? Voltage noise from 50 ohm resistor? Anybody? It's a nanovolt. So a 50 ohm resistor gives you a nanovolt. A nanovolt per root hertz is the noise from a 50 ohm from a room temperature 50 ohm resistor. And so what that means, what does that mean? That means that if you build a perfect aperture that's 1 centimeter, and it detects an electric field, let's say 1 nanovolt, let's say it detects a 1 nanovolt per centimeter electric field, and then you perfectly read that out over a 50 ohm resistor, the electric field sensitivity will be 1 nanovolt per centimeter in 1 second. That is the scale of what you can do. That's what you do with an antenna. You take an aperture and you read it out with a room temperature resistor that is subject to Johnson noise from the fluctuation dissipation theorem. So you see that we're not down to one. First off, you see that that's actually this line. So this line is basically that. You actually see if you have a resonant dipole antenna, it actually gets, I think, within 3 dB of that line. So this is what happens if you have a 1 centimeter dipole antenna read out into with sort of perfect impedance matching into a 50 ohm load. And you see that for this paper, that was maybe 3 to 5 dB better than the Rydberg atoms.
Would that have been equal thermal noise if your resistance had been 377 ohms instead?
That's a good question. If your resistance had been 300, there is probably no. If you changed the electrical impedance of your readout circuit, you'd used a bigger resistor. You could, in principle, would change your sensitivity to electric fields. Now, the issue is that the free space impedance is 377, and so in reality, you can't do much better than a numerical factor away from 50 ohms. And so I think, again, I can't prove that to you right now, but I'll just assert that whatever the sensitivity you would get from a 50 ohm resistor is within a numerical factor of the best you could do.
Oh, sure.
Yeah.
But you're not very far away from the
It's true.
limit.
It's true.
What I was wondering is that just because you didn't use the impedance of free space?
Oh, I see. Okay, so yeah, there may be a few more numerical factors that I've applied under the rug here. So here's another mysterious factor. If you're surrounded by black body and you build a collection aperture of 1 centimeter squared collection aperture, there's also noise on the input, just from the electromagnetic noise that comes from the black body that you're looking at. Come to find out, that noise is also within a numerical factor of what you would get if you then plug that into a 50 ohm resistor. All of these things are equal. And what this line actually is here, oh, sorry, I hit the wrong button. What this line actually is here, again, these things are, so within a numerical factor, everything I've told you is true, but I think the one place where maybe there was a little misunderstanding is this is actually external thermal noise, the noise that's actually assuming that you're in a black body and the noise coming in from the outside. But that's within a numerical factor of what you would get if you actually took the thing from it with no output noise and plugged it into a 50 ohm resistor. I'm sorry, that's a little bit confusing, but that's, again, kind of the thermal noise. That's the way to think about the electric field sensitivity that comes from everything in thermal noise. Now, so I think there's part of the answer here, which is this is complicated, and this gets complicated. Where do I think we are now? Right now, we're in a place where I believe that over this, if you want to build a system that quickly can achieve good sensitivity from 0 up to a terahertz, Rydberg atoms may be state of the art. They may be state of the art for very fast hopping or for simultaneous detection. I'll show you that in a minute. The other place where Rydberg atoms may be state of the art in the near future. So right now, it's very debatable if Rydberg atoms are state of the art for anything, but where they may be state of the art, man, I'm running out of time like crazy. Where they may be state of the art is also that there is no thermal noise inside of a Rydberg atom. There's no 50 ohm resistor. There's only quantum noise. And so as people are building better and better systems with more sort of atoms that you get to use, it is very likely that in the next few years, Rydberg atoms will be effectively cryogenic, that their internal noise will be less than what you would see from a room temperature 50 ohm or 377 ohm resistor. And actually, the first result from that came out from a Polish group pretty recently by one of a researcher I have a lot of respect for, Michał Parniak, who showed an effective internal temperature of a Rydberg sensor that was around 2 Kelvin. So that's a system that looks like you have that you've cooled it down on the inside, but you haven't. There's no cryogenics. You're just using the fact that these atoms are in non-thermal states. So, okay, there's a lot there. One of the other, last thing I'll show is one of the other really neat things that you can do with Rydberg atoms, and I'm really not sure if there's a way that I could, thank you. I'm really not sure if there's a way I could mimic this with other technology, is doing simultaneous reception. So in this experiment, we just take, in our case, 4 Rydberg transitions, and we play the game. We apply RF fields to all of them at the same time. And in this case, we use the superheterodyne technique that I showed. And by using the superheterodyne technique, we can give each of the carriers here its own modulation frequency. So it has its own modulation in the baseband. And so when we just take when we take the bare output of this thing and we put it on a photodetector and we take the FFT, we can see all 5 carriers here in the laser beam, in the FFT of the detected laser beam. And what I can say is actually those carriers range from 1 gigahertz to 117 gigahertz. So we have 5 carriers from 1 gigahertz to 117 gigahertz, and we have detected them all phase synchronously at the same time into one baseband. And I think that this would be actually quite difficult to do with reasonable sensitivity, or possibly with sensitivities we could imagine doing in a similar system. So this is kind of a more recent demo that I think is pointing towards some of the unique things that Rydberg atoms might be able to do. Okay, there's lots of other advantageous things about Rydberg atoms. They don't have any metal in them. You imagine people in the Army might care about the fact that there's just no metal in this system. That can be really useful. They are very easy to calibrate because in some sense their signals are related to first principles that you can calculate using quantum defect on a laptop in a few seconds. There's a lot of advantageous things about these sensors that people in the DoD are excited about. So there's lots of work right now towards transitioning them out of the lab. Even at ARL, we have work on physical test beds. We're thinking about putting these in a vehicle in the near term, and other companies are doing that as well. We also just came out with a modeling software that I'm really excited about. It's Python based, that can be used to give accurate forward models for how these sensors work. It's actually important here because you can use, even in this system I just showed you, we used 5 or 6 atomic levels. You can apply lots of local oscillator fields. You have moving atoms, and the thermal effects are actually quite significant. And so you really need a way to quickly move over the design space and understand the behavior. So we've recently emulated that experiment we did with 5 tones, and we recently did it in software. And actually, our software is released through the University of Maryland Quantum Technology Center. So I encourage you to go see our GitHub page. And yeah, there's another slide about that. And then the very last thing is that we are absolutely hiring. I would say if you're a US citizen, I would say it's a no-brainer. You should come check it out and look at it. If you're not a US citizen, you should still come visit. I wish that we could hire foreign nationals as postdocs, but at the moment we can't. So that's the unfortunate reality that is, not my decision. But I still think, recommend everyone come visit, and particularly if you're looking for postdocs or grad students. We've had 2 UMD grad students, actually. One of them's here, David. Oh, actually, Peter too.
Not didn't work there.
Oh, well, yes. We've had several very successful UMD grad students. One is, an award-winning Army physicist. Our other recent grad student that I was thinking of is still pursuing a career in physics and had a great experience. So we're open to hosting PhD projects as well, and that has been very productive in the past. So there's a lot of unique things about ARL that I like. It's really, it really gets you a peek behind the curtain of where a lot of DoD funding come from. I don't know the exact number, but I think over 50% of funding for research in our area comes from defense sector. And working at ARL, you really get to see a little bit better how things work and where money comes from, and then how the Department of Defense is looking towards us as scientists to make advances that will be useful in the real world. So yeah, so that's the end. And thank you. Yeah.
So you do everything with room temperature. Cold atoms, of course.
We have a cold atom experiment too that I didn't have.
Enough advantages to do that when you're thinking more about that stuff.
Yeah, I think so. I think there's definitely reasons to think about. So, okay, the fact that the atoms are moving around causes a lot of annoyances. I really don't know that. The real question is, I would boil the real question down to how many atoms can you get in a superposition of the ground state and the Rydberg state that you can read out at somewhere near the standard quantum limit. It is unclear that cold atoms are the route to do that, because there's a lot of atoms in a vapor cell. There's actually, really more atoms in a vapor cell than there are in a normal magneto-optical trap. So nonetheless, there are definitely areas where cold atoms could be useful. Actually, one practical thing I can think of is I hear that there are lots of real world scenarios where you don't want more bandwidth, but you actually want less bandwidth. You want a very narrow sensor that is locked into a signal with low bandwidth very precisely. And that can be hard to do with antenna-based systems, because they're very temperature dependent. They're not very well controlled. It's hard to calibrate them. And sometimes they just don't have high enough Q. I mean, it's hard to build an antenna with a Q that's above 1,000, but having an atomic sensor with a Q above 1,000 is very easy. So in situations that require high, low bandwidth, cold atoms could be very useful. There's probably a lot of other ones. That's just the one that came to my mind right away. Yeah. Yeah.
So if I understood well, this sensitivity scales favorably with the principal that we had.
Yeah, that's right.
What is the typical? And the reason I'm asking is that in solid state, also people have seen Rydberg
Yeah,
state.
that's right.
And is it promising evidence?
I have no idea. I have no idea. That's the.
No,
Oh, solid state Rydberg atoms, or?
yes. So from your experience,
Yes.
what is the typical end that you see some
Yeah, so we have the best sensitivity from n equals 50 to n equals 75. Is again, as you go higher in n, bad effects, first order and second order bad effects start to hurt your sensitivity more than the improvement from going up in n. And so the best sensitivities are in that 50 to 70 ballpark. Yeah. I don't know solid. I mean, I know very little about, other than just, I know that people work on Rydberg excitations in solid state systems. I don't know what the coherence times of those excitations are, what the, how well they interact with outside fields. I don't really know anything about that, but it's kind of interesting to think about. Yeah. Yeah.
So could you go to your slide that you spent some time on that showed all the different
Yeah.
sensitivity limits?
Yeah.
Right, okay, now, the thing with all the residences.
Yes.
Is this, 50 ohm dipole.
Oh, here.
I've understood correctly.
Yeah. Yeah,
Okay.
this is a 50 ohm, this
Right,
one.
So what's going on?
Well, this is you take a 1 centimeter dipole antenna and you connect it up to a 50 ohm resistor. And now what you find is that there is a specific frequency where the electrical impedance of that dipole is 50 ohms and it's impedance matched. That's right here. So that 50 ohm dipole that's 1 centimeter is actually a half wave right here.
Yeah.
And then you get to a frequency where there's a cancellation. And so this is just, again, this is not a be all end all plot. This is just to show you as an example what is the sort of canonical thing that happens if you take a 1 centimeter electric dipole and you read it out into 50 ohms without doing anything fancy. There's tons of games you can play for impedance matching, but this was more simple-minded than that. It's just what happens if you take 50 ohms, all right, a 1 centimeter dipole, plug it into a 50 ohm resistor and voltage readout. And actually that works very well at one point right here. But now you could imagine having impedance matching circuits that allow you to, smooth out this plot so that it has good sensitivity along this range. Although the fact is you typically can't do everything, right? That's the sort of the whole point of, RF physics is you can impedance match this very well over some range, but typically you can't make it ultra wideband. So that's kind of the way to think about that plot. Did that answer your question okay?
Sort of, but it
Yeah.
sounded like Nathan wanted to say something.
Yeah.
Well, I think maybe one question would be, you have this half wave and it looks like maybe the full wave resonant.
Yeah.
Understood.
And then
But then they kind of tail off. So I
Yes.
might have thought that the minimum of each of these things would be the same threshold of thermal noise or something.
No, I mean, again, remember, so you have this half wave, or you have this, we didn't change, you have a 1 centimeter. So imagine really that higher frequency thing, it's not a half wave at 1 centimeter, it's a half wave at a much smaller length. But now think about it, the voltage induced, that half wave dipole would be much smaller. So the voltage induced on that tiny half wave is smaller. So it's actually expect it to go up as frequency goes up. Think about it as what happens here is the higher order resonance is that you get uncanceled half waves. You have a half wave, you have a 3 halves wave. So it mostly cancels and you have a little bit of uncanceled wave there. And the voltage induced by that uncanceled part, it gets smaller. So, I think this mostly makes sense. Yeah.
So all that, all those places where it goes bad is where it's particularly badly impedance matched. Is that?
Yeah, exactly. That's all of the places where the wavelength set, which is 1 over this frequency, is an integer multiple of the length of 1 centimeter. It's a fraction of 1 centimeter, and you get complete cancellation of the field over the 1 centimeter. And again, this was just taken as one example curve, but it does illustrate something very important, which is that an antenna, just like a Rydberg atom, has discrete resonances. And unless you do something fancy, you're not going to be able to receive every frequency with one antenna. Yeah. Oh, David.
Just to add to that.
Yeah.
Kevin's right that the important at the feed point.
Yes.
So this model was done with the center fed.
Center fed. Yeah. Right.
If you did an end fed dipole assumption, then all of your resonances would actually swap.
Yes.
All the bad points become good points, and all the good points become bad.
So yeah, maybe there's some details I threw under the rug of like, where is exactly the feed point of this antenna? Yeah. Thanks, David, of course. Actually, all questions should go to David. Yeah, I'll just go ahead and just make that announcement.
Well, we should probably thank the
Yeah.
speaker again.